Hey everybody, in this video we are going to be looking at a couple of things about middle vision. I'm so glad that I got this marker that I can use now. I can just scribble all over the place. I feel like a little kid drawing on walls. Alright, let's move on. So middle vision, what is it? Like I mentioned last video, is basically the space in between the striate cortex, which is all about detecting lines, and before we get to the inferotemporal cortex. So before we get to really kind of complicated objects that we're perceiving. That space is middle vision. It's where we're going to be doing things like grouping lines together. It is where we are going to be detecting edges that are going to allow us to detect what's the figure and what's the ground of whatever it is that we see. So for example, you know this coffee cup is in front of the wall behind us, right? So that happens in middle vision. In middle vision, we're also going to be looking at how we can look at very rudimentary depth cues. So how can we detect that something is in front of us versus behind us? And also we're going to look a little bit at how we're able to see things making the fewest assumptions possible. In other words, how we're able to do this as quickly as we can. So one cool feature of middle vision, one of the phenomenon that we get out of it, is called the global superiority effect. And the global superiority effect is our tendency to really perceive the whole object over the tiny little bits of it first. So in other words, to put it another way, we're more likely to see, I know I'm rocking Starbucks today, even though you don't know that I'm a Dunkin' guy at heart. So, for example, if you were to see this cup, the first thing that your brain is processing is the shape of the cup, how big it is, etc. The second thing you're going to do is see the logo, right? So, the global cues are going to be the overall shape, and the form is going to be, or the local cues are going to be the little piece in the middle. So, our brains perceive the global cues first, which is why it's called the global superiority effect. So here what we're seeing is, if I were to ask you each of these, you would say probably all the time that this is an H, this is a C, and this is an L, even though what we're actually seeing is an H that is created out of several 5s or S's, an N that is created of several, a C that is created of several N's, and an L that is created out of several H's. So that's the global superiority effect. It's our tendency to notice the big parts first. Another very similar thing is called the dynamic superiority effect, and this is whenever we perceive things that are moving where we perceive things that are moving first before things that are not moving. So whenever something is rotating or when something is moving around, we are more likely to focus on it, we're more likely to notice it, and that's because movement is going to give us a little bit more information about what it is that we're seeing, and so we're not only going to be able to recognize this first, but we're also going to be more likely to remember it in the future. So that kind of movement is going to stick with us more often than not. This is something that happens in middle vision as well. These are easier to discriminate whenever they are moving versus when they are stationary. Let's talk a little about depth cues. Non-accidental features are features that tell us a little bit about where something is in the environment. So there are a couple of different cues here. What we're looking at here is, the first thing that we're looking at is a T-junction. You can kind of see a T-junction right here. Why is it a T-junction? Because it has this kind of letter shape right here. Basically what that tells us is that this the smaller line, the line on the bottom, is going to be the back. That's going to be the back part that is being occluded or being covered up by the longer kind of line. I always think of it as the roof of the T. So that's a T-junction. A Y-junction is basically whenever you have this right here, because again it looks like a Y. And when we see that, we perceive that that is a corner that is likely sticking out at us. It looks like that corner is facing us. And when we see this arrow junction, which is right here, called an arrow junction because it looks like an arrow, we assume that that is an angle that is pointed away from us. And so this is depth that we're able to perceive. We're able to perceive what's in front of what direction it's facing, just on these very rudimentary features. They're just lines and how those lines are connected to one another. Sometimes this stuff can be ambiguous. So for example, this right here is a Y junction, but it, depending on how you're perceiving it, doesn't stick out at you. And so you're more likely to see that this is sticking out at you than this, because we're kind of perceiving this gray to be in the background, that if this is a clear square, that the corner is pointed away from us. But again, that's why these particular kinds of squares, which are called Necker cubes, Necker cubes, why they're interesting to us, why they are fun to draw when we're kids, because you can kind of perceive them ambiguously. You can just as easily kind of imagine this as being the corner that's facing towards you, and this being the one that's facing away from you. Alright, so that's middle vision. Let's jump into some of the cognitive theories about recognition. I'm going to try not to spend too much time here because a lot of this stuff you'll probably come across whenever you take cognitive psychology. So, there are going to be two ways in which we're really going to talk about feature recognition. One of them is going to be called template matching. Template matching, what we're seeing here is this letter A. So what template matching tells us is that whenever we see this letter A, which is, again, just lines like this, that how is it that we're able to perceive this as the letter A? What template matching tells us is that we've seen this so many times that we've created a template for it. And that template is in our visual cortex, it's in our striate cortex. And so whenever we have, and what you're seeing here, these circles, you can imagine those as being separate neurons. So when you have this neuron, and 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 this neuron active, then you perceive an A. Okay, that makes sense. But here's the problem. What if you saw that slightly angled in a different way, which is what you're looking at right here in some of these examples in the bottom, or even over here in this example, for example D, which is kind of hard to see because of my big dumb head. But so in this case, this is the letter A, but template matching would say that we don't recognize that as the letter A because it doesn't fit onto this neuron and this neuron and this neuron and then this neuron and this neuron. I'm not going to keep going, but you get the idea. It's not mapping perfectly onto that, and so what template matching theory tells us is that we probably wouldn't recognize that as the template. Template matching basically, and so that's the template for A is because it's hitting those neurons, and for L, it's hitting those specific neurons that we have learned signify L. Okay, great. But there are a lot of problems with template matching, and that's why it's not really favored like it used to be just a few years ago. People were really into it because they found that they can develop machines, they can develop software that recognizes text and recognizes pictures because of template matching. But even though that's true, we can see how there's a lot of limitations in computer software compared to our own visual processes. So for example, if you think about like the CAPTCHA, security things where you have to like type in, those really kind of crazy letters, the idea is that software can't tell what those letters are, but we can. And if that's true, then that means that, well, maybe template matching isn't what we're doing because we know these machines are using template matching and they're not working out. So we know that's probably not true, so the other side of things is what's called feature analysis. Feature analysis theory is much more simple, and basically it's that we're not really remembering templates. Instead, what we are remembering is the combination that these visual features have in common. So for example, whenever you learn what the letter A is, what you're actually learning is that there are 3 lines involved. A line that goes like that, a line that goes like that, and a line that goes like that. And so if you put it like that, that's an A. If you do it like this, that is an A. If you do like this, that is an A. Because what you're really learning is that there are lines angled a certain way, and whenever those lines that are angled a certain way occur together, we perceive them as a letter. And so even though I said this is more simple, I feel like it's more simple to understand, but it's a much more complicated process than what template matching theory is. This is much harder for computers to do because it's really kind of complicated. And yet, this is something that our brain kind of takes for granted, right? It seems really easy. So the evidence for this is that we're much more prone to make mistakes whenever there are numbers and letters that share visual features. So for example, C and G, we commonly misconstrue, right? Because a G is basically just a C with a mustache, right? It's got this little mustache right here. A B and a D, we're likely to perceive them incorrectly because they're just kind of mirror opposites like that. You get the idea. That tells us that what we're learning and what we're responding to is the relationship that these letters have, that these lines have in common. So this is kind of what our science feels like is the most accurate way of looking at this. It's really hard for us to be 100% conclusive about that, though, because in order for us to do that, we basically need to go in and surgically remove parts of people's brains, and we can't do that ethically. And so we have to rely on these really kind of complicated behavioral tasks and neuroimaging to help us understand, to the best of our knowledge, how these things work. All right, the final bit of the final part of the cognitive theory section of this chapter is about what's called recognition by components. And recognition by components is the theory by Irvin Biederman. And Biederman had this paper that came out in the 80s, so 30 years ago now, that basically, or over 30 years ago, basically showed what he believed was how our brains put together information, put together lines. So if we're assuming that feature analysis is correct and we know that middle vision is correct, we're moving higher than those things. So in this case, we're talking about how we are able to learn that this is a cup, or that this is a fierce dragon. Don't ask why I have a dragon on my desk. Don't ask about that. Here's how it works. Basically, we have three parts of this process. We have three parts that feed into how we are able to recognize objects. The first part is going to be that we're going to break this object down into sub-objects. And so we have, and again, this will be familiar to people who have taken cognitive psychology, you're seeing this, and you're concluding that that is a horse. You're seeing this, and you're concluding that's a giraffe. But while we do that, we're kind of breaking it up, and so that its face is shaped like this, its neck is shaped like this, its torso is shaped like this, its arms are shaped like that, its legs are shaped like that, its tail is shaped like that, and etc. And the same for humans and for ostriches and things like that. All right, so whenever we see this horse, we're breaking it down into its sub-objects. When we do that, then we are going to take those sub-objects and we are going to categorize them. We're going to put them into different categories, into something that's called a geon. So you'll see this word in your book. Basically, it is short for the word, boy, it takes a long time to draw this stuff out, for geometric ions. So geometric ions is what geons is short for. And so basically we have 36 different kinds of geons. Here's a couple of examples of what they might look like. We have a cylinder here. That's a very basic shape. A football shape, a cone shape. You get the idea. So there's 36 of these different ones. And according to Biederman thought that this is basically as simple an object as you can get. You can't reduce a pyramid into a smaller sub-object, according to Biederman. So in other ways, you can kind of think of them as elemental shapes, that all shapes are built out of these elements. And finally, what we do is we recognize the pattern in which those objects are put together. If you're interested in more about how that works, you have to take cognitive psychology. We're not going to go into a whole lot of detail here about that, but what that basically means is that we are, let's see, here's a disgusting fish that my dogs like to play with. So we have a fish right here. It doesn't even really look like a fish. So we got this fish right here. So if I didn't tell you what it was, but I asked for you to recognize or try to recognize what it is, you would say a fish after much deliberation. And that's because you're breaking this down into its sub-objects. You got a fin up here, you got the eyes, you got this tail over in the back here. And so you are seeing this as multiple objects. You're going to classify, okay, this is kind of a fin shape, this is kind of a fin shape, these are circles, and this whole thing is a circle. And so you would recognize those sub-objects, and then you would recognize the pattern in which those sub-objects had in common. So for example, here with this human, what you're doing is you are recognizing the sub-objects. You're classifying, okay, we got a cylinder here, we got a cylinder here, a cylinder here, etc. And then you recognize like, oh, the proportion of those cylinders tells me that that is a human, because we can see all those same sub-objects, all the same geons here, but we would not classify this as a human being, right? And that's because the proportions are slightly different. And so we're recognizing the proportions in which those geons have when you put them together. All right, so that's all that I want to talk about for cognitive theories about object recognition. We're going to close this chapter up by talking about face perception next. All right, bye.